Okay, so now we're going to begin homework 2. I'm going to try to favor using nodal analysis instead of the universal method thing that Reza teaches, just to give you guys a little bit of a insight into some different methods. Um, but they all basically come back to Kirchhoff's circuit law, Kirchhoff's voltage law, all that kind of stuff like that. So anyway, in this circuit, our task is to find the output, well, the VO, which in the next course, VO usually denotes the output voltage of a system. So I'll just call it VO. And then verify, oh sorry, we need to find I1 and I2, then VO. And then verify that power developed equals the power supplied, or dissipated. So anyway, first step is we see these, we go and see, okay, these two are here, this is here, and this is here. So these are different voltages. We have our V out, we'll call this V1, and well, let's just say this is our ground node. This is 0 volts. So we know that we have 1.5, let's say this is like I out. We have I out equals I1 plus I2. Well, if we go back to Ohm's law, V equals I times R, we're going to have V out minus 0 over 100 for 100 ohms, and then V out minus V1 divided by, well, actually, one thing we can do to make this a little bit simpler is we can notice that these two resistors are in series. I don't know if he's taught the addition rules and everything for them yet, but real quickly, when you have resistors in series and they will equal the sum of their resistances. So if we have 100 right here, or I'm sorry, 150, and then 250, that's going to be 400 ohms. So we can skip this entirely. We can come back to find that later, actually, just to be thorough. So anyway, we'll have V output minus 0 with this R equivalent. Let me put that in a different color. Say this is our R equivalent over 400 equals 1.5. I'll do a little bit of algebra. We'll see that we have, let's see, let me get my calculator. This is 1 over, we'll factor out the V out first. So V out is going to be 1 over 100 plus 1 over 400 equals 1.5 amps. So let's see. 1 over 100 plus 1 over 400 is 1 over 80. So 80 times 1.5 is going to be our output voltage. So that means that, let me write it out, 80 times 1.5, because this equals 1 over 80, equals 120 volts, which equals VO. So we found VO kind of in reverse than what the problem was asking for, but we can find all this information the same way. Because once you solve for one thing in these circuits, you just plug and chug. So anyway, to find I1, we're going to do V equals I times R. So we're going to have our V is 0 divided by 100. So that's 120 divided by 100, which equals 1.2 amps. And since we know that I1 plus I2 equals I0, they're 1.5, so we have 1.5, 1.2. That means that I2 must be 0.3 amps or 300 milliamps. So from that, we can find out the value of V1 pretty easily. Because if we know that the current through we know this current I2 is going to end up being 0.3 amps. We can do it we can find out V1 one of two ways. We can either look at the voltage drop across this resistor or the voltage drop across this resistor. Either way will work, but I'll show both. So anyway, V out minus V1 equals, over 150 equals 0.3. So we do 0.3 times 150, and then we we add V1 to the other side. So V1 equals, let me do that again. Let me do that, write it down just so there's no confusion. So we're going to go to, this is 45 equals V out minus V1. So to find V1, we can just put V1 on this side and then subtract 45 from VO, which we had determined previously as 120. So 120 minus 45 is, I think, 75? Yeah, it's 75 volts. We can also find the V1 by using the same KCL, because I2 is shared by both of these resistors here. So that means we can find V1 the other way. If we have V1 minus 0 over 250, then it's pretty much a straight shot to find I2 or V1. You just multiply 0.3 times 250 and you get V1 equals 75. Both of those will work. It's mostly a matter of convenience, but like I said, once you find one of the values in the circuit and you know it's right, because it makes physical sense, there's nothing crazy going on, then you're golden. So to verify the total power developed equals the total power dissipated, well, that's just going to be, if we take all these resistors, multiply their voltage drops and everything, we could find the total power dissipated. So we can do that. If we make, so the V out right here, the voltage drop across the 100 ohm resistor is V out minus 0 times the current I1, and that'll be the P, let's just say that's P1. So let's see, 120 times 1.2 is 144 watts. And then we'll consider these two resistors together just to save a bit of time. So we have VO minus 0 times I2, and I2 is 0.3 times 120, which equals 36 watts. We also have this current source over here. Well, we have the current flowing from minus to plus, so it's going to be minus in the front, and we have 120 we have 120 volts across it and 1.5 amps. So that is, I think, 180 or minus 180. Let me double check real quickly. Times 1.5. So yeah, so we have 180 plus 30, or negative 180 plus 36 plus 144 equals 0. So the total power developed equals the total power dissipated, and we have successfully solved this circuit. So for problem 2.20, we're going to follow it up the previous problem using a similar process. Number one thing we're going to do is identify the nodes in the circuit. We're going to see where things are connected and see, okay, well, these things, they share that, they share that, they share that. You don't have to circle them, but I'm going to circle them just so you see what I'm talking about. Just remember that whatever you have connected is connected. Anyway, so I'm going to set this as my ground, my 0 volts. Let me do that again. So I'll say this is 0 volts. It doesn't matter where you put your ground. It's completely arbitrary when it comes to the circuit analysis. In a real circuit, it will be important because you'll generally be designing something and they're all going to reference each other. Anyway, I'm picking this one to be 0 volts because that will make our V output, or make this node load voltage our V output, or V0, whatever you want to call it. So anyway, this will mean that it's 5 volts right here. That means it has to be minus 5 volts over here. Now, why minus 5 volts? It's because if this is the positive terminal, this is the negative terminal, and you consider the top terminal to be 0, in order for this to be actually 5 volts, then it would have to be minus 5 volts on the bottom side. If you put the ground reference over here, for example, that would make the voltage at this node 5 volts and this 0 volts. It's completely arbitrary and up to you, but I chose, for the aforementioned reason, to put the ground at the bottom. So anyway, we're going to do something called nodal analysis for this. It's a different technique to solve circuits than the universal method, and it may give you a couple insights into different ways to solve a circuit. It'll also, you may find it easier, but it's always up to you. Just make sure you get the right answers. Anyway, in nodal analysis, we assume all currents leaving a node are leaving, even if they aren't actually leaving. Because we know, in this case, that the current has to be going this direction, because the source is pushing it that way. Well, it doesn't have to be, but in this case, it does. Sometimes the currents going this direction can be higher than the current source is providing, but not in this case. You'll know because other circuit, your KCL will tell you. So we're going to assume that all currents are leaving. We're just going to name these currents. So this is I out, here's I1, and here is I2. So we'll write our equations up here. And we have I0 plus I1 plus I2 all equals 0. V equals I times R. And since we have currents, we're going to try to solve for the currents. So to do that, voltage drop divided by resistance equals I. And I2 is known. And since it's flowing opposite of the little arrow, we're going to call that negative 20 milliamps. So let me write the rest of the ones first. Anyway, so the I0 is going to be V out minus 0 over 5,000. We have plus, and I1 is going to be V0 minus negative 5 volts over 2,000 ohms. And then we have minus 20 milliamps equals 0. This could also be represented as 20 times 10 to the minus 3 amps. They're equivalent. It's up to you. So first thing we're going to do is push the 20 milliamps to the other side, and then we're going to multiply everything by 5,000 because it's the biggest number. It'll clean up all of these denominators, make it a little bit easier to solve. So this is just going to become 1, and then 5,000 divided by 2,000 is 2.5 times V out, and then the minus is canceled, so this becomes plus 5. And then we have 20 milliamps times 5K, which is 100. So we're going to multiply this out right here. We're going to see that 2.5 VO plus 12.5. Just multiplying 2.5 times, we're distributing the 2.5 basically. So we're going to combine terms. We're going to get 3.5 V out plus 12.5 equals 100. Then do a little bit more algebra. V out is going to be 100 minus 12.5 divided by 3.5. And we're going to find out what that equals. So 100 minus 12.5 divided by 3.5 is 25. So V out is 25 volts. We've completed the first task of our problem. And now that we have V out, we're going to test our solution for V out. We're going to make sure that it makes physical sense. And the way we're going to do that is we're going to find the total power in the circuit. So to do that, we're first going to need to know the currents flowing through these different nodes, or these different resistors, I'm sorry. And I'm going to draw this as this is also I1 because they share the same, they're in series. All right, so to find I out, just going to do 25 minus 0 over 5,000. And I believe that's like 5 milliamps. Let's see, 25 divided by 5,000. Yeah, that's 5 milliamps. And we're going to do the same process for I1. 25 minus 5, which is plus 5, divided by 2,000. I think that's going to be like 15. 30 divided by 2,000 is, yeah, 15 milliamps. Okay. Well, that seems to be making sense because we have the 20 milliamps over here. So we're definitely getting things balanced. So let's go and check out the power throughout the whole circuit. All right. So to find the power supplied by the current source, let's say that let's just say this is P1. So we have a voltage of 25 volts across it and 20 milliamps flowing through it. So if we say that this is the plus and this is the minus, and the current's going this way, we're going to have the minus over here. So 25 times 20 milliamps equals 0.5, oops, let me put the minus, equals 0.5 watts. Let's say P2 is the power supplied by the battery, or the voltage source. So we're going minus to plus, we're going to have minus up front. We have 5 volts. Let me put the unit just to be clear. 5 volts times I1, which is 15 milliamps. So let's say this is 15 milliamps. All right, so 5 we got 75 milliwatts. So 0.075 watts. Okay, so we know our power is supplied. Now we're going to find the power dissipated. This one we'll just use I squared R to save a bit of arithmetic. All right, so for P3, which is going to be the power dissipated by the 5K resistor, it's going to be I0 squared times 5,000. So that is 5 milliamps times 5,000, and that is 0.125 watts. P4, same process. 15 milliamps squared times 2,000 equals 0.45 watts. So if we add all these up, we should get 0, unless I made a mistake. All right, so plus this minus 0.5 minus 0.075 equals 0. All right, so we know our solution for VO makes physical sense because we're not getting any more energy out than we put into it. We've successfully solved this problem. All right, so for 2.22, we're going to try and do a little bit more nodal analysis, try and familiarize ourselves with it. Okay, so number one thing we're going to do is identify our nodes. We got a node here, we got a node here, we got a node here, and we got a node here. So all of these are shared connections with these different components. So we can find, well, I'll set this as my ground, which will automatically make this 80 volts. Doesn't matter where you put your ground, but generally it's a good idea to put it where there are the most number of connections. Because generally, in a circuit, that's going to be ground anyway, especially in this case, because we have, it makes this 80 volts right away, one less voltage we have to worry about. So anyway, we're going to call this V1 and call this V0. Then we're going to do KCL at each node. So in nodal analysis, we assume that the currents are leaving always. We assume that our node is at the highest potential. Doesn't matter if it isn't, it just means that these currents will be the opposite direction ultimately. So I'm going to call this I1, I2, I3. These are just so that way you know what I'm talking about when I'm writing the equations out. So anyway, KCL at V1, I1 is going to be V1 minus 80 divided by 13 plus V1 minus 0 over 4 plus V1 minus V0 divided by 4 equals 0. I'm going to do the same thing at this node V0. So it's going to be I1, I2, I3. These are not anything other than just names I'm giving them, so you know what I'm talking about when I'm writing the equation. So V0 minus 80 divided by 8. And then we have V0 minus V1 divided by 4. And then V0 minus 0 divided by 20 equals 0. Okay, so this one, we have two equations and two unknowns. So we're going to set up a system of equations and solve it. Now this one is going to end up being pretty hairy to solve by hand. It is possible, but it's just a lot of fractions and gives you a lot of chances to make mistakes. So what's the first thing I'm going to do is put this into a form that you can really put into a calculator. Some things, like I believe there's I forget what it's called, but he gave everybody a website where you could basically punch in equations and they would solve them right away for you. But I'm going to put it into a way that my calculator can understand. I have a linear solver on my H3 prime. You can also do this using matrices or matrices, but frankly, the linear solver is easier. So anyway, I'm going to take V1, or the KCL at V1. I'm going to copy that down. Let me select it. Well, I'll just circle. Okay, so the first thing we're going to do is multiply everything by 13. So we're going to have V1 minus 80 plus 13 over 4 V1 plus V1, 13 over 4 V1 minus V0 equals 0. I'm going to multiply everything by 4 just to get rid of that fraction. So 4V1 minus 320 plus 13V1 plus 13V1 minus 13 V0 equals 0. Put these all together. So we got 30V1 minus 13V0 equals 320. Okay. And we're going to do the same thing for the other one. We're going to pull it down, multiply it by 20 first. So 20 over 8 V0 minus 80 plus 5 V0 minus V1 plus V0 equals 0. Multiply everything by 8. So 20 V0 minus 20 V0 minus, what's 20? 1600? Yeah. 1600 plus let's just do this again. 20 times 8, 20 times 8. Yeah. So I'll just say that this is 20 over 8, which is, I think, 2.5. Yeah. 2.5 V0 minus 80 times 2.5, 200 plus 5 V0 minus 5 V1 plus V0. And we're going to multiply everything by 2 just to get rid of that 0.5. So 5 V0 minus 400 plus 10 V0 minus V0, V0, V1. Yeah, okay. Just want to double check. 10 V1. And then there's 2 V0. Right? Oh, duh. Okay. I made a tiny mistake. Just let me write it all down. So ultimately, the thing simplifies to be minus 10 V1 and then minus, plus 17 V0 equals 400. So I'm going to plug that into my a linear equation solver in my calculator, I'll be able to get V1 and V0. You could do this by hand using elimination and substitution, things like that, but it's just way faster to use a calculator. So I punch that in, minus 10x plus this, plus 400, plus 30, minus 13, plus 320, and we get that V1 equals 28 volts, and V0 equals 40 volts. So from that, we can find I1, which is the number one thing we need in the problem. So I1 is going to be V1, which is 25 minus 0 over 4, so it's going to be 28 divided by 4, which is 7 amps. And might as well find I0 while we're here. So V0 minus 0 over 20, that is 2 amps. Okay, so now we have 2 amps, we have I1 and I0. We can find the rest of the currents in the circuit pretty easily with Kirchhoff's circuit law, or Kirchhoff's current law. Alright, so let's solve for, actually, we can just do voltage drops. We don't even have to find the other currents for finding the power. Okay, so the power dissipated in each resistor. We're going to do that one by one. So if we have this 8 ohm one, let's call that P1. P1 is going to be the voltage drop across it. So 80 minus V0, which is 40. Or no, sorry. We're going to use V squared over R for that one. V squared over R, because that way it'll save us a little bit of trouble calculating the current. So P equals, in fact, we can calculate the current. I don't know why I'm worried about that. Because we have the voltage drop across it. Okay, so let's say that this is I don't know, I2. We'll do it the 30 different ways, just that way we can get all of the different ways you can calculate the power. So this one I'll do as the I squared R. So I2 is going to be the voltage drop across the resistor, so 80 minus 40 divided by 8, which is 40 over 8, which is 5 amps. And yeah, 40 divided by 8. Yeah, okay. That's 8 ohms. All right, so to calculate the power, let's call that power 1 again. That's going to be 5 amps times 40 volts dropped, 200 watts. That's a really, really big resistor. Okay, so 200 watts. Let's say we want to do, the next one is, call this P2, the 15. So I got the voltage drop across that one. We're going to do that one directly. So P2 is going to be 80 minus 28 times, we'll do the V squared over R. We'll do V squared over R for this one. So 80 minus 28 squared divided by 13. So 80 minus 28, 52 squared divided by 32. Okay. So 84.5 watts. And we're going to do this one Let's say this is I squared R because we already have it calculated. So that one will be P3. So I squared, I1 is 7, so 7 squared times, what is it, 4 ohms? Yes, 4 ohms. So 49 times 4 is 196. And P4, let's call that the last resistor, or there's 2 more resistors. Okay, so say this is P4. I'm going to do the voltage drop again. And it's the magnitude of the voltage drop. So we're going to do 40 minus 28 squared divided by 8, 4, divided by 4. 40 divided by, or no, 40 minus 28. So 144 divided by 4 is 3.5. That one's actually the most reasonable resistor here. Interesting. Okay. So I did that calculation right because it's just really low. 28. Let's do that one more time. 40 minus 28 is 12, and then divide that by 4, 3 amps. Yeah, I made a calculation mistake. What did I do here? I did 14 divided by 4. That was my bad. Okay, that is supposed to be 36 watts. Okay. I knew it looked wrong, especially with that low resistance. Okay, and then the last one, we're going to call this P5. That's when we're going to do I squared, or because we already have the I. So P5 is going to be 2 amps squared times 20. So that's 480 watts. So we're going to add up all this P1, 2, 3, 4, 5, blah, blah, blah. 80 plus 84.5 plus 196 plus 36 plus 200. Now I'm going to double check P2 one more time just to make sure, because it does make some sense, but I want to make sure. 80, yeah, 80 minus 28 squared, B squared over. Let me do the current real quickly. So 80 divided by, or 80 minus 28 divided by 13 is 4 times 13, 52. I made a mistake. I had a feeling they'd all be whole numbers, and I was right. Just pays to double check your calculations sometimes. Okay. So we have 52. That means the total power dissipated should be 564. Unless I made a mistake again, that should be right. And we want to make sure that the power dissipated equals the total power developed by the voltage source. I'm going to double check these again. 40. P1 was that, right? V squared. 80 minus 40 divided by 8 times 5 amps times 40 volts dropped 200 watts. Okay. Yeah, I have to double check these calculations. I want to make sure that I'll be right back. Okay, yeah, I found out what I did. I just skipped a step with the calculator right here. So this is just me being silly because we did all the hard math already. So 2704 divided by 13 is 208. I just skipped a step in my head. I did 80 minus 28, which should be the voltage drop. Anyway, so add them all up, we get 720 watts. And we want to make sure that they pass the power check. So the power supplied is going to be the current flowing from the power supply times the voltage across the power supply. And we got two currents here. Let me erase this so you can see them. We have I0 and I1. So I0 plus I1 is 9. 7 plus 2 is 9 amps. That's going to be IS. So IS is 9 at 80 volts. So 9 amps times 80 volts. And it's supplied. So minus 720. So yeah, power check passed. All right. So this one's, I think, the hardest one in this homework assignment, mostly because of the kind of tricky math here, but it all comes back to fundamental stuff. If you can understand what's going on, then it's just the math where you're going to trip up. The math is where people usually trip up, even myself. As you can see, I make arithmetic mistakes sometimes, and second guess myself, etc., etc. So nobody's perfect, even somebody who passed this class with an A. So let's move on to the next one. Okay, 2.23 is a little bit easier than the previous problem, namely because we're given a little bit more information and it's not as many nodes to analyze. But we're still going to circle them so we can recognize them. We're not going to really bother too much with the nodal bit with this, because we're only trying to find a couple things and we're given a little bit of information that makes it easier. So anyway, one thing we can do here actually, we want to set this to be our 0 point. And we know that the problem gives us 90 volts dropped across this resistor, and we're supplied 240 volts. Well, 240 volts minus 90 volts is 150 volts. So this node in particular is at 150 volts. Anyway, let's first find the currents through these resistors. So we'll say this is I1. This can be I2. I'll put I3. And we'll say I4 is this one. Let me do that again. Let's say that this one is I4. It's kind of cramped. I'm sorry. Let me do that one more time. I4. And then I5. All right. So now we're going to solve for I1 first. I1 is going to be really easy. It's going to be 240. Oh, we don't even do that. We just know it's 90. So 90 divided by 22.5. That's going to be, I think, 4? Let's see. 90 divided by 22.5 is 4 amps. Okay. So we can calculate the power right away, but I'm going to get the rest of the currents first. Let's find I2. I2 is going to be 150 divided by 15, which is 10 amps. And then now we can do a little bit of KCL and find out I3. So I1 plus I3, or plus I2 plus I3. Let me actually do it the other way, just to be a little bit less confusing. Because we have I3 and I1 are coming in here. They're both entering that node with a 150 volt node, and we have I2 leaving. All right, so if we have 4 amps coming in plus I3 plus, or not plus, equals 10, then I3 must equal 6 amps. So if we know that I3 equals 6 amps using Ohm's law, then we can find out, using Ohm's law, we can find out the voltage over here and quickly find the other currents. We can also use KCL to find those currents, but let's just do this real quickly. Okay, so if we know I3 equals 6 amps, we have and we're going in that direction, so that means we'll call this V1. V1 minus 150 divided by 5. So 30 plus 150, V1 equals 180. And that makes sense. We have 30 volts dropped across it. Divided by 5 is 6. So now we can calculate I4. Let's say I4 is 180 volts divided by 20 ohms. Oh, I'm sorry. 0 minus 180 volts divided by 20 ohms. That's going to equal minus 9 amps. So that means that, in fact, I4 is flowing this direction, but we drew the arrow that way, so it's minus. All right. So the magnitude of the current is 9 amps, which is the important part for calculating the power. And then I5. Well, we have I4 and I3. So we can actually do KCL for that one, or we can do Ohm's law. And I think we can do Ohm's law just to save a little bit of arithmetic. Okay. So we have 240 minus 180. So 60 divided by 4, I5 is 15 amps. Going the opposite direction, actually. Let me flip that, because I5 is going up. 980 minus 240. So minus 15 amps. But the magnitude is important for the power. All right. So if we know all the currents in the circuit, and we know all the information, we have all the information we need to calculate these values. So I'm going to do this being 1, 2, 3, 4, 5, just like the currents. So P1 is going to be I squared, or is going to be 4 squared times 22.5. So that is, I think it's 360. Let's do it. 22.5 times 16. Yeah, 360 watts. P2, we have 10 amps times 15 ohms. So that's 1500, I think. 100 times, yeah, 1500. P3, we 6 amps times 5 ohms, 36 times 5 is 150, I think. 36 times 5, 180. Then P4 is going to be 9 amps squared times 20 ohms, so 81 times 20, that is 162 times 10, 1620. Double check that. Yeah, 1620. And then we have P5. That is 15 amps times 15 ohms, so 225 times 15. This one I can't do in my head. 3375 watts. So I'm going to add them all up. 360 plus 1500 plus 180 plus 1620 plus 3375. We have 735 watts. So unless I made a mistake, that should be what we get for our power supplied. So number one thing we're going to do, we have 15 amps going this way and 4 amps going this way. 19 amps. 19 amps times 240. Yeah, I may have made a mistake when it comes to P5 because that's a really high one. Let's double check this. So 920, 15 times 15. Does that make sense? Oh, you know what it is? I did times 15 instead of times 4. So 225 times 4 is 900. So that would make this whole thing. Yeah, okay. Gotta be careful with your resistors. I saw 15, and made it a little mistake. If you caught that, good. Congratulations. You were paying a little bit more attention than I was. Alright, so that means that the total power dissipated by the resistors is 4560 watts, which is consistent with the power supplied, which is 19 amps times 240 volts, which is 4560 watts. So yeah, the power supplied does equal the power dissipated. And we successfully have solved this circuit. Okay, so for 2.24, I accidentally cut off a little bit of the problem, but if you have the textbook, you'll be able to see it. I1 is given as 20 amps, and I2 is given as 15 amps. And our task is to find the power supplied by each voltage source, and then we're going to find out if the power supplied equals the power dissipated. So let's go ahead and let's just draw these currents. Now, since I2 is lower than I1, there's a good chance, no, not a good chance. Sorry. We will know that we're going to know that I4 is probably going to go this direction. Or not I4. Okay, let's call this I3. And call this one I4. This one I5. And this one I6. They might end up being the other ways around, but we're going to just assume that at first. So we're going to do the case, let's just say this is node 1. or node 2. This is going to be node 1, and this is going to be node 3. So 1, 2, 3. All right. So the KCL at node 1, we have I1 going in, and I2 and I3 going out. So we know I1 is going to be 20. And we have I2 is known to be 15. That means I3 has to be 5 amps. That's good. So now we can start to calculate the other values in the circuit. So let's do a KVL for this loop. I'm going to try and find out what I5 is. Or not. Not that one. Because they're not given enough information yet, I don't think. Okay. So say that we pick this loop right here. We're going to do a KVL. Consider that a closed loop. And say that inside we got the 80 minus, or sorry, 80 I6 minus 16, because we're flowing opposite this little kind of, let's call it a mesh current. The mesh current right here, we'll say that our little loop is going this direction. So I2 is flowing opposite of it, so it's going to be minus. And so minus 16 I2, and then we're given, once again, minus, so 8 times I1. Okay, and this is all going to equal 0, so we have a closed loop. So let's plug it in. We're going to do 80 I6 equals 16 times 12, or 15 plus 8 times 20. So let's punch this all in. 16 times 5, 15 plus 8 times 20. It's 400 divided by 80. I6 equals 5. Okay. So now that we have I6, we can go and calculate the other stuff. Because we got I3, we got I2, so we need I5, and we need I4. Well, let's do a KCL at node 1, or at this node, I guess. Or, sorry, yeah, KCL at, yeah, it is node 1. I just wrote the wrong number here. KCL at node 1. So we have I4 going in, and we have I1 leaving, and I6 leaving. So I4 is going to equal I1 plus I6. So I1 is known to be 20, because it's given by the problem, and I6 we just calculated as 5. So I4 is 25 amps. And then let's do the same process over here at KCL at node 3. We have I2 going in, and I6 going in, and I5 leaving. We know I2 and I6, so it's 15 plus 5 equals 20, which equals I5. Okay. So let's look at these one more time, make sure we got everything good. 25 and I got 20. Yeah, all these answers make sense. Everything's going in the right direction. Okay. So the current flowing through the power source up here, we got I4. This has to come from, because these share the same node up here. So I4 is that. So we can find the power supplied by 240s or 230. So let's say let's say that's P1. That's going to be I4 times 230. So we just calculated I4 is 25. 25 times 230 is 5,750 watts, or 5.75 kilowatts. Once again, we're going to do, to calculate the other power, we're going to do the same process. So the current flowing through this, the current flowing through the 260 volt, come on pen, work please. Okay, I guess my pen, the color one, doesn't work right now. I'll fix that in a minute. Anyway, so we have I5 going through here, but we also have I3 going through here. So if we have I3, now we have I3 going in, and then yeah, I'm sorry. Okay. Let me do that one more time. We have power 2 is going to be 260, and then we have I5 is going to be 20 amps. So 20 times 260 is 5,200, or 5.2 kilowatts. Okay, so that makes sense. That one seems right. I'm going to be right back. My OneNote is bugging out, so I'm going to close it out, and then I'll come right back. Okay, so we got the first step problem, or the problem completed. We had found the power supplied by each voltage source. Now we're going to make sure that the circuit is consistent. So we have all these things, currents, blah, blah, blah. And we're going to add up all those currents. And I think you know the drill in terms of how to calculate this, but in case you need a refresher, since we already have currents, we're just going to do I squared times R to find the power dissipated by each resistor. So the power dissipated by the 8 ohm resistor, let's say that is P1 because of I1. Yeah, we'll keep the naming convention with the currents. So P1 is going to be 8 times 20 squared, so 8 times 400. That'll be 3.2 kilowatts. And just do this same process for I2. I2 is 15 So 225 times 16, 3600. And then, let's see, what do I call I3? Okay, so I3 is 5 amps, so 25 times 25 times 4 is 100 watts. And say we have, where is P4? Or I4? I4 is 2 ohm resistor, so we have 25 amps. And then, okay, so 625 times 2 is 1250. P5, we're going to do I5, which is 20 times 2, or 20 squared times 2, so 400 times 2 is 800. 800 watts. And P6 is, let's see, I6 was 5 amps, 25 times 80, 2000. Okay, so now that we have all these values, let's add them up and make sure that they don't exceed 5200 plus 5750. So I'm going to do that real quickly. 5200 plus 5750. That's our total supplied power. Then I'm going to subtract each of these values. So minus 3200, minus 3600, minus 100, minus 1250, minus 800, minus 2000. This should be 0. Yeah, okay. So the power check, yeah. Power check makes sense, and we have solved the circuit. Just a little bit of KCL got us a long way. And if we wanted to, we could calculate the voltages really easily because we already have the currents. We just use Ohm's law. We can find every voltage in the circuit real quickly. Okay, so for problem 2.26, our task is to find the value of this unknown resistor and then the power supplied by the 240 volt source. So basically what we're looking for is we want to find this voltage and this current so we can calculate R. And we can do that if we can find the other values in the circuit. So we'll do that in a minute. And then we also want to find out what the current supplied by this power source is, and we can figure out the power supplied. So number one thing we're going to do here, identify nodes. Node here, we got a node here, node here, node here, node here. Don't get intimidated because we can get rid of half of these pretty much right away. First thing we're going to do is I'm going to call this 0 volts. That's our ground. It is automatically going to make this 240 volts. And then we can find this voltage over here by using Ohm's law, because we're given the current through that resistor right away. So V equals I times R, we can find the voltage drop. We have 4 amps, 4 amps times 5 ohms is 20 volts. That means this is 220 volts right here. So now we've simplified our problem a lot, made it way simpler. So let's call this V1, V2, and G3. You can also note that I can find V2 really easily by that same process. Because we have 4 amps going this way. There's nowhere else for the 4 amps to go because these are 2 resistors are in series. So let me write the 4 amps right here. So if we have 4 amps going through that 10 ohm resistor, the voltage drop across that resistor is going to be 4 amps times 10 ohms, which equals 40 volts. Now, what is 220 minus 40. It's 180. So that means V2 equals 180 volts. Now we can't use that trick anymore, but we do have a little bit more information that'll make the rest of our work simpler. So if we consider that we have these closed loops and everything, we can do a little bit of nodal analysis. So if, say, we're going to do KCL at V1. So let me do a different color in case I do another one, so that way we don't have to worry about mixing things up. Okay. So we're going to do a KCL at V1. So V1 minus 240 divided by R, and then V1 minus 0 divided by 10, and then V1 minus V2 divided by 4 equals 0. Oh, sorry, V2 we know. Okay. So now we can actually do a little bit of trickery. Make this even easier. If we have these two resistors in series, 14 plus 16 ohms is 20 ohms. So the voltage drop across that is known because these two are in series. So the voltage drop across them in total, we don't have to worry about V3 anymore, because V3 won't give us any information other than the current through that resistor, but it's the same current through that resistor, or it won't give us any information except for the current through this resistor, but we know that, so why would we bother? Anyway, so V equals I times R. We have 180 volts dropped across our equivalent of 20. So that means we have 9 amps flowing through that node. Which means if we have 4 amps going this way, and 9 amps going this way, that means we have to have that 5 amps made up over here. So if we have 5 amps going that way, and that means we have 5 amps leaving, which means that V1 minus 180 is going to equal 5. So let's do that real quickly. V1 minus 180 divided by 4 equals 5 amps. So we have 20 volts. That means V1 equals 200 volts. Okay. So if we know that V1 equals 200 volts, let's put that here. Now we can find the current flowing that 10 ohm resistor. So 200 volts minus 0 divided by 10 equals 20 amps. And since we have 20 amps going this way, 9 amps going that way, we found our supply current. We also can figure out what R is. Because if we have the 20 amps going that way, 5 amps going that way, that means that the current through this resistor has to be 25 amps. So if we know that we have 25 amps going through that resistor, 25 amps going through that resistor, we also know that the voltage drop across that resistor is going to be 240 minus 200, so 40 volts. And we can use V equals I times R. Let me actually put this over here. V equals I times R. And we're going to solve for R, so V over I. 40 volts divided by 25 amps. I believe it is 6 something? 5? I don't know. Hold on. 40 divided by 25. 8 over 5, 1.6. I had a 6 in my head. Okay, so that is our R. And we can double check, see if that makes sense. If we have all these resistors, blah, blah. Yeah, that makes sense. Because you have 4 amps going into that one. And the ratio between them, so 5 divided by 1.6. Oh yeah, that's also the voltage drops too. Okay. So 1.6 amps makes sense for this answer. And now we have our R that we needed. Now let's go ahead and calculate the power supplied by the source. That one's going to be super simple. Since we already calculated all the other currents in the circuit, 29 amps times 240 volts is, what is it, 29 times 240, 69.6, or not 69.6, 6960. 6960 watts. And there we go. We've successfully calculated both R and the power supplied by the source. Okay, so for problem 2.23, or 33, sorry, our task here is to find the VO, the like sort of output voltage, I guess, and the total power absorbed in the circuit. So this is a two-step process. Now, I believe this is the first problem where we have a controlled current source. This one happens to be voltage controlled. So whatever the voltage drop across this resistor is divided by 100 is the amount of current flowing through or being supplied from that current source. It's nothing super fancy, it's just another representation, basically kind of like a control system. So you can envision this as sort of like your input, and this is your output of your circuit. Say you were trying to get, say this was like a potentiometer or some kind of volume knob or something like that, and say that this was for a voltage-controlled amplifier or something. Anyway, that's being way outside the scope of this course. Number one thing we're going to do is identify the nodes in the circuit. Okay, so this one we already have a name, it's VO. I'll call this ground because it's a common reference. That makes this 20 volts right away, and this is VX. All right, so first task is to calculate Vx. There's a lot of different ways to do this. The easiest one would be to use the voltage divider equation, which, if you're unfamiliar, is your voltage output equals your voltage input times the ratio of the bottom leg of the voltage divider plus the total voltage there. Now, it's not written like that in this circuit, but let me draw a voltage divider real quick. Let's say that here's our input. There's R1, R2, and this is ground. It doesn't have to be ground, but it's just your bottom leg. So here's V out, and here's V in. R1, R2. So if you notice, we have R1 and R2 here. Now you can also go back to your fundamentals, the UKCL and everything, and just solve that. You have two equations, one unknown, and solve right away, all that stuff. But if you are comfortable with that, you understand your fundamentals pretty well, you can save a bit of time by taking this sort of shortcut. I know Rez is not a big fan of them, but it will help you when you get to more advanced courses to understand this concept. Anyway, so if we call our V out Vx and our V in is 20 volts, and we know R2 is 150, and what's 150? Sorry, let me do it in order just to not be confusing. So we have 450 for R1 plus 150 for R2, and if you do this math, you'll end up with Vx equals 5 volts. Let me double check that. Let's see, 150 over 600 is a quarter, yeah. So yeah, this answer, it makes sense. So with Vx, we can calculate, say we want to call this Ix. Doesn't matter what we call it, but I'm going to call it Ix. Well, Ix is being supplied by this source, and that's value, the magnitude of Ix is determined by Vx over 100. So if Vx, sorry, if Ix is that relationship, Vx divided by 100, that means we have 5 volts divided by 100. Well, let me get rid of the units. Let's just consider it like that. So I believe that's 20 milliamps. Let's see. Or no, not 20 milliamps, 50 milliamps. 5 milliamps, not 50 milliamps. Okay. So 5 divided by 100. And that equals 5 milliamps, or 0.00. Oh wait, no, it is 50 milliamps. I'm sorry. I did it right in my head. Okay, so 50 milliamps, or 0.05 amps. They're the same. So anyway, now that we have that, we have nowhere else for the current Ix to flow but through this 300 ohm resistor, right? This 300 ohm resistor right here. So to calculate VO, all we have to do is Ohm's law. So we have VO equals Ix times R. So that is 50 milliamps times 300 ohms. So 300, that means that VO is 15 volts. Okay, so we solved the first part of the problem. Now we're going to solve the second part of the problem. Okay, so we have to find the total power absorbed in the circuit. So we're only worried about the resistors, not worried about the sources, even though they would end up being the same amount of power supplied as dissipated. Okay, so here we can do another bit of trickery, because these two resistors are in series, so they share the same current, so we can add them up to find the total, like their equivalent resistance. So 450 plus 150 is 600 ohms. That's the REQ for that first one. And we have 20 volts. So 20 volts divided by 600 ohms is, I think it's going to be like a repeating number. Yeah. So 33.3 milliamps repeating. Let me double check. Yeah. Okay, so that would be, let's call that I1. And since we know I1 and the voltage drop across it, so P1 is going to be I1 times 20 volts. So that times 20 is going to be 666 milliwatts for P1. And a similar process for P2, which is going to be the power dissipated by the 300 ohm resistor. But we can just use our 15 volts times 50 milliamps. And that equals 0.05. 750 milliwatts. So that plus 750 plus 6.67. The total power is going to be, let me just write in watts, 1.4166 repeating watts. So there we go. We got all the things we needed in the circuit. We used a little bit of trickery to save us some time, and maybe learn a new thing along the way. For 2.34, we're given a similar process or similar problem to the last one. We want to find this voltage drop across this resistor and the power supplied by the circuit. So there are two supplies in here we're going to consider. There's the dependent voltage source and the ideal current source. So those two are both going to supply power. We'll consider those later in the circuit analysis. So number one thing we're going to do, identify our nodes again. Now, we don't necessarily have to worry about the sort of grounds. But let's say, because we're only looking for a voltage drop, but let me just say that this is the ground reference. So this is going to be V1, and you know what, actually, let's not worry about that. I don't want to get too confusing. This one's actually a pretty simple problem. But just remember those are the nodes. So anyway, we can do KCL here to find out what the voltage drop across this resistor is. So let's say that this is like IS or I supply or whatever. And then we have IX and we have I0. So I0 is going to be the current flowing through the 2 ohm resistor. So anyway, we got KCL. Let's call this, let me put the node labels back. Let's call this node 1, 2, and 3. So KCL 1, we have IS, IX leaving. Well, let's just go IS first. IS going in, and then IX leaving, and IO leaving. So we know IS is going to be 45 amps. So let's just go ahead and plug it all together. So it's 45 amps equals IX plus I0. But let's actually come up with a quick expression for I0. So I0 is going to be, remember Ohm's law, V equals I times R. So if we want to find the I, we get to divide V by R. So we have V0 divided by 2 ohms. So let's go ahead and put that into the equation here. And we want to find IX because IX is going to be, or the V, this voltage over here, is going to be dependent on IX. So anyway, if we go ahead and double everything, so we get 2IX plus VO, we can get an expression to find the whole sort of thing. Anyway, so if we have IX here, let's consider this as a loop. This, I'm going to draw a little arrow. See, here's our loop. And it doesn't matter where we start our loop, but I'm going to start at this point here. So anyway, we're going to do KVL. So you have VO and then 2 times IX. That's the voltage drop across the resistor there. Or sorry, that's the voltage. The voltage right here. That's the voltage. And then we're going to have a voltage drop of 6 times IX. So all of that is going to equal 0 if we consider that the green loop is a closed loop. So if we take this whole expression, we're going to end up with V out equals 4IX, which means that IX equals V out over 4. So we have an expression for IX in terms of VO, and we can plug that back into our original equation. So let's have 90 equals 2IX, so 2 times VO over 4 plus VO. Now we have only one unknown. We can solve this pretty quickly. So we're going to multiply everything by 2, 180, and equals VO plus 2VO. Now, if you get confused, I took this in and notice there's going to be a half whenever I took the 2 in. So I multiply everything by 2 to get rid of that half. Anyway, that means that VO equals 180 divided by 3, which equals 60 volts. So that is our hysteresis we got VO. Now we're going to calculate the power delivered by the whole circuit. So once again, we're going to go back and notice, okay, we got these 2 sources, so we got to account for each of them. I'm going to say that P1 is the current source. So we have 45 amps times the voltage drop across this resistor. So the voltage drop across that resistor is known to be the voltage drop across that resistor is going to be 6 ohms times IX. And if we remember that IX expression over here, that means that IX is 15 amps. Because VO, let me just calculate that real quickly. 60 volts divided by 4 equals 15. So we can plug in 15 over here. And we're going to have a minus because there's a increase in voltage across this sourcing power. So anyway, let's go ahead and calculate all this. I think 60 times 15 is 90, so 90 times 45 is 4050. So I'm just going to put it in kilowatts just to, because it's a big number. So that's P1. And P2, we use a similar process. We're going to have 2IX, which is the voltage supplied by that source. And then we have you have to consider the direction of the current. So if there's a voltage drop across IX here with IO going this direction, then we're going to have a plus up front. And we're also going to have IO. So we know IO is going to be V out over 2. Let me use a different color for that. V over 2. So we don't have to really do any math, but we can. 60 divided by 2 is 30. So that means that we have 2ix. So 2 times 15 times 30. I believe 30 times 30 is 900. Let me double check. Yeah. So we have 900 watts being consumed or dissipated or absorbed by the dependent source. So even though this is a source, it's not truly supplying power to the circuit. So power supplied equals P1. So we have 40-50 watts being supplied in this circuit. Now don't worry so much that the source is dissipating or consuming power. It doesn't violate any laws of physics or anything. It just means that instead of sourcing current, this is sinking current, which is something that happens a lot of the time in electronics. Okay, so for 2.36, this one looks very, very intimidating because you have 3 dependent sources and 2 independent sources. But it will ultimately go back to your fundamentals and everything sort of makes a little bit more sense. So anyway, number one thing I'm going to do, identify nodes. I'm not going to worry about necessarily a ground reference here. We can, but it won't necessarily make it easier. Because these voltages will change with the currents, so it doesn't necessarily make it automatically going to make this 12 volts or make this minus 8 volts if we set this bottom one to be 0. So number one thing we can do, so I'm just going to label this current, call this one I1, and we already have I delta here. I'm not going to worry about that. I already have I sigma right here. And let's call this I2, I guess. And then we have this is a current source, so we're given that. We'll just write this as, let's call this the voltage across this V1. Because we're going to need all of these values to calculate the power developed, which is the second task of this question. Anyway, number one thing we're going to do is consider this closed loop right here. So we're going to start up here and just make a loop of all the voltage gains or losses across this loop. So to do that, we're going to have, let's call this 1. We're going to code KVL1, or for loop 1, I guess. We have a gain of 12 volts. If we go from the minus to plus as a gain. Then we're going to have a reduction, but not necessarily a reduction, but we're going to just call it that. Because actually, it is a reduction, because we're going plus to minus. So yeah. It could end up being the other way around, but for now, we're going to call it a reduction or a drop. And then we have the voltage drop across the resistor, just because it's a resistor, so 5 times says I delta, right? Oh no. Yeah, okay. And all of that's going to equal 0 to that loop. We're going to do another one, because we have 2 unknowns here, so we need one more equation. We're going to do another loop, and we're going to call this one, let's call this loop 2. So KVL for 2. This one is going to be let's start at this top corner. So we have going plus to minus, so 8 I sigma plus 2 I sigma to 2 ohms times I sigma. And then we have minus, because we're going back up here. So minus 5, because the current is going opposite of it, of our little loop. We're going to have a minus, and we have I delta, not sigma, sorry. So minus 5 I delta equals 0. Okay, so this is we can right away notice we got a kind of a relationship between these two. So if we put 5 I delta on one side as your plus, add 5 I delta to both sides, then add these two together, you get 10 I sigma, which means if we take the ratio, we have I sigma is going to equal 1/2 of I delta. So I delta over 2. So that means that 2 I sigma equals I delta. So now we can plug back in to our first equation. We got an expression for it. So let's do the KVL thing again. So minus 12. I'll only put the 12 on the other side because it's negative. Okay, so 2 I delta equals or 2 I sigma equals I delta. Well, we have a 2 I sigma right here. So we can just put in I delta. So I delta in that place plus 5 I delta equals 12, which means that I delta equals 12 divided by 6, or 2 amps. So that's one more thing we've solved. So now that we have I delta, now that we have I delta, we can go back and put that into this equation. And we'll find out that I sigma equals I delta, which is 2 divided by 2, which equals 1 amp. So now we've got pretty much all of the information that we need to solve the rest of the circuit. So we can find out that if we found I delta, now we got to find VO. Now to find VO, we're going to use Ohm's law. VO equals I sigma times R. So I sigma is known to be 1 amp. So 1 amp times 1 ohm is going to be 2 volts. Okay, so now we've found all of the things we need for part 1. Now it's just a matter of cleaning up. So we're going to come back to these things I labeled earlier that I said we would need to calculate the power. And that's not too bad. It's just a bunch of Kirchhoff circuit law and then some power. Anyway, so I'm going to do KCL for, say, let's do KCL at this node right here. I'm going to call this 1, 2, 3, 4. So if I do this as KCL at 2, we have I1 going in, and we have I delta going out, and I2 going out. So if we can go back to see this, I sigma blah blah. That means that I2 is going to equal I sigma plus, I sigma plus 8 I sigma. Yeah, 8 sigma. 8 sigma. Yes, because there's I delta. Right? Yeah, sometimes the Greek letters are confusing. Okay. So if let me go back and think for a second. So we have I sigma. So we got this going in, this going out, and that's going on. Yeah, because the current source. Okay. I confused myself for a second because I saw the voltage I drew earlier. So I2 is going to equal I sigma plus 8 I delta. So you have an expression to calculate these various currents. Anyway, so let's go back and put that. Let's go ahead and put this in to there. So we're going to have I1 equals I delta plus I sigma plus 8 I delta. Oh, that's not a delta. So we're going to use the values that we calculated earlier. So 9 times, I believe it's 2 plus 1. So 18 plus 1 is 19 amps. So that's our I1. And that means we can calculate the I2 pretty easily. Because we know that if we know I1, and we know, I1 is known to be 19 amps. Let's go back to our original KCL. So we want to calculate I2 now, which is as labeled before. So we know I delta to be 2 amps. That means that I2 has to equal 17. That's just 19 minus 2, 17 amps. Okay. So now our task is to find the voltage over here. We're going to consider this third loop. We want to find the voltages, and we have the currents and the voltages so we can calculate the drop. So let's go ahead and do our V1 as a drop because the current's going through it in our little loop. And we have a gain of 8 volts going from plus to minus, or minus to plus of there's a voltage source. Then we're going to come back out, and there's the drop VO that we calculated before. All that has to equal 0. So if we know VO from prior calculations, we can just do this real quickly. So V1 equals 8 plus VO. And VO is known to be 2, so 8 plus 2 equals 10. So now we have everything we need to calculate the power. Let me just move these down real quick so I have more space. Okay. So the next step, we're going to find the power that is developed by this source. So we know that these currents are positive, so we're going to be going plus to, or minus to plus. So it's going to be definitely a gain. But let's just do the magnitudes to save a bit of time. It doesn't make a big difference here. So we're going to call that P1 for the 12-volt source. So if I1 is 19 amps, and the voltage is 12 volts, 19 times 12, that's 228 watts. So let's find another power. Let's just do the voltage source over here. That one's going to be pretty simple because we know the current flowing through it right away because we calculated it. So we have the current going through it 8 times I delta. So I delta is known to be 2 amps. So 16 amps times 8 volts equals, I think that's a power of 2. Let's see. Yep, that's 128 watts. Okay. So the power, yeah. Okay, I'm sorry. We have to do more than just calculate the power developed. We also got to calculate the power absorbed. And we're just going to show that they equal each other. Check our sanity check, I guess. So we can say that the power supplied is going to be P1 plus P2. So P1 plus P2 is 356 watts. That's our supplied power. So anyway, we have how many of the elements in this circuit? We have 5 more. So we're going to have to do 5 more simple little algebras. So we got a drop, a drop, a drop, a drop, and a drop. Yeah, I should have mentioned that before, how I knew that those are definitely going to be the only 2 supplying, is because the direction of the currents. We have voltage drop across this, voltage drop across this. Anyway, so the resistors are easy. We're going to have, let's say, P3. We're going to have, what is it called? Say P3 is the 5 ohm resistor. Power dissipated by that. So we're going to have I delta squared times 5. So I delta is 2. 2 squared times 5 is 45 watts dissipated. I'll say P4, just we'll do a resistor because it's easy. I sigma squared times 2. So I sigma is 1 amp. 1 squared times 2 is 2 watts. So now we can do the voltage sources. I think let's just do, yeah. I'll do the current source first. So I'm going to call the current source, say that's P5. Don't get confused, this is an S, not 5. Let me change this to be a little bit more clear that that's an S. That might be better. So P5 is going to be the power for the current source. So 8 times I sigma. I sigma is 1, so we'll just do 8. And V1 we calculated as 2 volts, I believe, 10 volts? 10 volts, yeah. So 10 volts, so 80 watts. Right? No, because it's I delta, not I sigma. My mistake. 8 times 2 times 10, it's going to be 160. Pretty sure. 16 times 10, yeah. Okay, so we're going to do the voltage sources now. So I'll call this P6, and we have We'll start with the 8 I delta one. It doesn't matter which one, but I'll just do this one. So 8 I delta, the current flowing through that is I2. So I2 is known to be 17, right? Yeah, 17. And the voltage across it is 8 times I sigma. I sigma is 1. 1 times 8 is 8. 17 times 8 is 136. And finally, P7. We're going to do the same process one more time. So 2 I sigma times I1. Well, I sigma is known to be 1, so 1 times 2 is 2. And the current flowing through it is I1. I1 is 19. So 2 times 19 is 38 watts. So we're going to add up all these, say this is power dissipated. I'm going to add up all the powers we just calculated and see if it matches up with the power supplied, which it should if I did the math correctly. So 128, or not 128, 45 plus 2 plus 160 plus 136 plus 38, 381. Let me double check my math, because that doesn't make sense. 30, 25, 38, 136, 2. Oh, I made a tiny little mistake here. Good job if you caught it. For some reason, I delta plus thing. I consider this a 3 in my head. That's actually a 2. So 4 times 20, or 4 times 5 is 20. Sorry about that. Let's do the math again. So 20 plus 2 plus 160 plus 136 plus 1 or plus 38 equals 356. So power supplied equals power dissipated, and we did everything correctly. You just got to be careful, because even I, somebody who's taken this course before, and like the 3 courses that come after it, even I can make silly mistakes like that. So just double check if it doesn't make sense. Maybe you just made a simple mistake. All right, so the final problem is 2.37. It looks a little intimidating, but trust me, it's not too bad. The number one thing we're going to take into account is the hint. The hint helps a lot, actually, because typically we're working from here and then getting over to here. We want to find out what a value is in the circuit before we say, like if this was like an output or whatever, we want to find out with respect to this input. So the solution here is we're going to work backwards. Number one thing we want to do is kind of hard to notice sometimes. I actually don't always read the problems myself whenever I do textbook problems, because I don't always have the textbook. But we have a given value for VO is 5. So that's going to simplify things a little bit. I'm going to put this as a node. This is a node. This is a node. Another node. Another node. And I'm going to call, just as we're given VO, I'm going to call this our ground, which is automatically going to make this 5. So make this VG, V1, and V2. Call them whatever you want. This is what I'll call them. So I'm going to label a current here, call that I0, call this one I1, and we'll say this is I2, I3. Let me draw that one more time. I3, Oh, I1's already taken up by another label. Okay, so I can't use that. So let's just call that, this one we're going to keep as I0. We have I1, I2, I3, I4, I5. Now, we don't necessarily have to do that, but it'll just have a common language for this problem. So I'm going to do a KCL first at, let me label these nodes. 1, 2, 3, and 4. So the KCL at node 1, we have the 40 I2 leaving, I0 leaving, and I3 leaving. One of these is going to end up being negative. We'll find out which soon enough, but I can pretty much automatically tell you that it's going to be this one. Just because we have, if we set this as 0, and the plus is over here for the VO, that means it's in current flows from plus to minus, that I2 has to be negative. We'll use the math to confirm that later. Anyway, let's do KCL at node 2. So we have, what is it, 20 I2 leaving. I put the 0. We have I4 leaving and I5 leaving. All those equal 0. And you can do a KCL over here, but there's nowhere else for the current flow, so it's just going to be I1 for both of those. Okay. Now I can start with the circuit analysis. So we're going to take our first equation over here, and we're going to look at I0. So I0 is going to be V0 divided by 40, and what did I call this? I3. So I3 equals 5, or VO divided by 10. So let's go ahead and put everything together. 40 I2 plus 5, that's VO, divided by 40 plus, is it 40? Yeah, it's 40, okay. Plus 5 divided by 10, yeah, equals 0. So 5 divided by 40 plus 5 divided by 10 is 5/8. So we're going to subtract 5/8. So minus 5/8. Then we're going to divide by the 40 in front of I2 to find I2. So I2 is going to be divided by 40, 1/64th, I think. Unless I made a quick mistake. Did I make? Let's see. Because 5 over 40 equals 1/8. And then plus 1/2, 625. Yeah, okay. That means that I2 has to equal minus 15.625 milliamps. Okay, so now that we have I2, and we can use that to work forward. So we want to find out what V1 is. To find V1, we're given this current here, and there's a voltage drop across these resistors. Since these resistors are in parallel, the voltage drop across them is going to be the same. So V1 is going to be, well, first thing I want to do, the voltage drop across that. So 25 times I1 is going to be, let's see, times 25. It's going to end up being let's see. I2. Oh, I'm sorry. I was looking at the wrong one. So V1 is going to be, oh, I2 is right here. Okay. So I2 equals I4. The diagram is a little confusing. So I'm just gonna scratch that out. Call that call that I2. That was my mistake. Anyway, let's move on. So we know I2 equals I4, or whatever. So to find V1, V equals I times R, so I2 times 80. 80 times negative 15 milliamps. Okay. So that's going to be minus 1.25 volts. So that means that the voltage over here is 1.2 volts higher than voltage over here. So if we call that the bottom one 0 and V1, let's go to KCL2. So we have KCL2. Now let me once again change this to I2, and I'll rename I5 to I4. If you skipped forward in this, it's going to be a little confusing, but I just didn't notice that this was going through that. I thought it was going through the entire top node. Anyway, so we have our KCL and everything. And we're going to try and find out what I1 is, because we need to find I1 to find VG. So, KCL2, this is not 20, this is 25. 25 I1 plus I2 is known, and I4, we can do a quick equation. That's just going to be V1 divided by 20 ohms. So let's go ahead and put in minus 1.25 volts divided by 20 ohms, and plus the 15.625 milliamps. Do our whole KCL together, I'll be able to find I1. So let's go ahead and plug these numbers in. They're a little bit confusing numbers, but don't worry, they work out just fine. So divided by -1 plus 15 points. Oh, I put the wrong sign here. Okay. So that means that we have I1 equals 0.078125 divided by 25, and that is, let's see, 0.07125 divided by 25. Okay, so I1 is 3.125 milliamps, or 0.07125 0.3 or 0.003125 amps. Okay, so to find VG, we're going to do the I times R once again. So if we have I1 and times 60 plus I1 times 260 equals, or VG. I can factor that out. So I1 times 60 plus 260. So I believe that's 320. So 320 times 3.125 times 10 to the minus 3. That means that VG equals 1 volt. So I believe that is everything here. So found V1 and VG when V equals 5. So we've solved everything in the circuit. A little bit of trickery, but it all goes back to your fundamentals, your KCL and your KVL and everything else. You just have to be careful when you're doing that, the analysis, and you'll be good. So I hope that these solutions have been able to help you guys out with homework 2, and it'll help you as you go forward with the next homework sets.